Okay, so we are very happy today to have Professor Raphaël Ponge. He is a professor at Sichuan University since 2019. His research interests include non-commutative geometry, global analysis, pseudodifferential operators, cyclic homology, and semiclassical analysis. He received his PhD from University of Paris-Saclay under the supervision of Professor Raphaël Ponge. Prior to moving to Sichuan University, he held faculty position at Seoul National University, Tokyo University, and University of Toronto. His research was published in various international journals, including Advanced in Math, Communication, and Mathematical Physics, Creel Journal, Journal of Functional Analysis, Memoir of AMS. He received a 1,000 Talents Award from Sichuan Province in 2020. Let's welcome.
So let's accept Sebastian and Jason for opportunity to visit BIMSA and to speak in this seminar. So my talk about the question about non-commutative geometry and Semiclassical analysis. So I won't really explain what is non-commutative geometry or Semiclassical analysis. We will get more details in my colloquial talks this afternoon. So Semiclassical analysis. The Semiclassical analysis. So I'm interested in the idea of Schroeder operators. So here, if you c'est le Schroeder operator en Rn. L'état de la prochaine, so la prochaine will be positive. And these potential, c'est a function continuous. Yeah. And S square is a stand for the Planck constant, and Semiclassical analysis, look at the behavior of the Schroeder operators when the constant Planck goes to zero. And particularly, you can look at the number of negative eigenvalues. So if H is a self-adjoint operator, it is negative divided by n minus H, the number of negative eigenvalues continues. Dans le cas de Schroeder operator n, propriété, this corresponds to the number of bound states. And you have this symmetrical variation, which goes back to the symmetries and even 60 is the case of operator on Rn or bounding domain Rn. So here I said the result for closed Riemannian manifold. So closed Riemannian manifold. We mean a compact only. And so it is a real value function, so continuous real value function, exponential. We can look at the number of negative eigenvalue of Schroeder operator, square delta G equals V. So delta G is the adaptation of 60 different metric. So if you think in terms of, then also think of the adaptation on a bounded domain where we take this direct effect of Riemann function. You count the number of negative values of H square delta G equals V, and H goes to 0, that's number of the limits. This is like H to minus n. So if you multiply H to the n, as H goes to 0, this converges to an interval which depends only on the negative part of the so it means interval of V minus to the power n of 2. And usually this is the domain. So you can have a domain in space. This is just and more generally, you can consider a fractional Schroeder operators. Where I look at the negative eigenvalue of H to Q delta V to V equals V. Take number of negative eigenvalue, we try the H again, and this is also going to converge to an interval that depends the one interval of some power of the negative part. This can
If you have just a differential operator of some order, they say not necessarily Laplacian to the power q.
Yeah, that works too. I mean, that's important that it's positive. So if you're elliptic, yeah, that's absolutely true. So it's going to one because yeah. And there are different ways to prove this also. So in fact, use the differential technique and actually even get some lower and yeah, precisely. Yeah. And another way, which is to use the Birman-Solomyak principles. So the Birman-Solomyak principle is useful if you want to extend the symmetrical ratio to a non-continuous potential. Because then you can use perturbation theory for which you can test. And so, if we set the Birman-Solomyak principle, this will be at the root of my talk. So again, H is bounded below with discrete negative spectrum and denoted by n minus 1 H number of negative eigenvalue with C. And what does the Birman-Solomyak principle is to write the statistical ratio to satisfy for asymptotics for eigenvalues of compact operator. So if A is the quadrant of compact operator denoted by lambda j plus or minus the positive or negative eigenvalue. So if you like, precisely on the J plus, this is the number of negative eigenvalue of the positive part, right? And on the J minus, these are the eigenvalue of the negative part. And so the Birman-Solomyak principle says that, so if you assume that H0 is positive or negative, and E is the Riemannian. So you don't need to assume H0 and need to be bounded. What you should have is that if you compress V by H0 to the minus monad, we get the compact operator. So this is going to ensure that square plus H0 plus V is going to have discrete negative spectrum. And here you make an extra assumption and assume that not only it's compact, but it's also it's on reach at class. And what is FP infinity? I didn't write. So a set of flat compact operator so that the eigenvalues of absolute value of t are big O of j to the minus 1 over p. So this is in fact the banal ideas. And Birman-Solomyak principle say that the extents of a limit as h goes to 0 of h here and number of negative eigenvalue of h squared 0 to 3 is equivalent of to have some kind of ratio for the negative eigenvalue of this Birman-Solomyak operator, which is namely it's equivalent to having a limit is equivalent to having a limit for j minus number j minus of f0 minus 1 f0 minus 1. And so that one limit exists, the other exists, and the two limits in another. So there is a problem of proving spectral value to follow some spectral asymptotic for some type of compact operations. And in fact, Birman-Solomyak prove ratio for positive and negative eigenvalue of self-adjoint and negative order of differential operators. And particular example of the following result is that f is a free valued function includes any positive number. Then you have a ratio for the positive and negative eigenvalue of delta g to the minus 2 over 4, f delta g to the minus 2 over 4. So if you apply on j plus or minus of delta g minus 2 over 4, f delta g minus 2 over 4 by j for the equivalent. J plus infinity is as in needs, which is given by some power of the integral or some power of a positive or negative part. In fact, this is a general result. Here you can apply delta g by mu. elliptic topology. Because this is the most important, this is actually the experimental function factor, and then you can apply the ratio of Birman-Solomyak for the function. And so you combine this with the Birman-Solomyak particle, and you get the symmetrical ratio. Again, the first line, this is the Birman-Solomyak principles, and you get from the top to the bottom line by applying the method. So this reduces the proving a symmetrical ratio to proving asymptotics, asymptotics, so I'm going to do this normal field effect. And kind as a note, this approach can be ordered in a very great geometry. In particular, it works for non-commutative manifold. So, in non-commutative geometry, in the sense of curve, non-commutative manifolds are given by so-called spectral tripod. So, what's a spectral tripod? So, spectral AHD. So, where H is a separable interface, A is a little star, so that's one LH. So here you see an algebra, the star algebra, represented by bounded operator H. And D is a separable operator with compact, which going to commute with the amount of algebra A up to bounded operator. And we say that, so I get some examples the sides. And let's correspond to the notion of dimension, it's a so-called T-symmetry. So you say that spectral tripod is fixable if the eigenvalue of D is like the eigenvalue of D are like the objects in this one look. So that exactly means that the eigenvalue of D is in the Wigschatten class LP. So in particular, the connection implies that mix minus 2 is precise for all Q return. So examples, so I will give examples for Riemannian manifold. So one example you can take is to take the square root of the functions. So Euclid's space is the space of the two functions, and as a part of the square root of the functions, the algebra A is algebra of smooth functions, which is represented by one indication operator. So that's a simple. So we can also for sums can represent by bounded domain. And replace then the Laplacians, as well as the Laplacian, as square root of the Riemann of the straightforward. And you can also replace the square root of the Laplacian by the diagonal. So the same example you can find many examples in non-commutative geometry, because then can do you have a full index. Well, we can also learn more information when we use the operator and when we use the square root of the. Yeah, for this talk I will use the square root. And all these protocols and symbol were n in the dimension of. So, right. So the main result is that we have a symmetrical ratio for spectral under some additional conditions, which is that you have some covariant. So you can give two covariant conditions, so they are related to each other in the sense that the second covariant condition implies the first one. So maybe you focus on the second conditions. So the fact that, so we assume that AG is a p-symmetrical triples. So it implies that the resonance of D is in a Wigschatten class. And this also implies that e to minus t d square is just class for all positive t. And so if you fly by any one of algebra A, this remains a just class. So what will work over that as t goes to 0, this is like t to the minus q2 times coefficient of A times some coefficient, depending on A, that what else to. All right, so this condition is satisfying numerous faults. And can also give weaker conditions in terms of residue of some zeta. So what we get is that so for triple is a p symbol. So it means that delta minus 1 is an LP infinity. And this is going to imply that d to the minus z is tres class. So tres class. Real part of z greater than. Okay. So you see that look at the zeta function of A is element of A. So this is a bounded operator. So if you look at trace to h to minus e, so this is going to be trace class for also real part of z greater than. So you yeah. So you have PE, the complex plan. So this is definition of the zeta function, and so what we require is that that's some meromorphic extension to some alpha space real part of z greater than p minus epsilon, epsilon positive, and with only simple pole singularity at z equal p. Okay. So this is what I mean for this function. Yeah. So if we have a second condition, we get first conditions. And both conditions are satisfied in the state. So if you have this, one of these conditions holds, then we get vice law for some Birman-Solomyak operator are superior to the. So let me if so here A bar, you see the closure of A in LH. Okay. So this will, so if you think of A as a bar of the smooth function, the closure will be like this is some. So for any continuous in the bar, I need to do 2. So we get the various asymptotics for the positive and negative value of x minus 2 to A, x minus 2 to 2. So if you apply the value by j to the cube of p, j goes to infinity, it's going to convert to some powers of positive, well, some powers of tau of some power of positive or negative. So here A plus A minus and minus 4 is synchronous of absolute value of A plus and minus A. Okay, so this, so you get a sketchfile something for Schrödinger operator, and you know that by the Birman and Schrödinger principle, this implies so many for all self-evident on B of the bar for all Q, represent the bar negative value of H to Q. D to the 2Q plus V by H to the P converges as H goes to 0 to lower power negative. And once again, the second part is the consequence, the second part is sur le flow, et selon the consequence of the first part by the man Schrödinger principle.
What is law? What is law? Oh.
So that's yeah. Tau is the coefficient of T, or this is
The definition of tau is the derivative.
Yeah, so, okay, so in practice, yeah, tau comes from the examples.
Wait, this is the definition of tau.
Yeah, that's the definition of tau, but it's usually in a concrete example, tau will be given, will come with a spectral triple.
Okay.
So for instance, when I take spectral triple as the equation, it will be given by the integration against and we'll see that. So I give an example next with a non-quantum Tori, and this will be a canonical trace. So yeah. But okay, so what you can see, so what you can see from this condition, so implies that tau is a positive trace. Okay, so let's look at previous result of McDonald Sukochev-Zanin. So the main improvement is that Sukochev-Xiong-Zanin assume that P is bigger than 2. And so this condition is removed. So the problem with the condition P greater than 2 that successful the two-dimensional example such as quantum Tori. And quantum Tori are the main instances of quantum motor. And also replace the tolerant function I mentioned are satisfied in many examples, and these are fairly standard domain function. And they give another domain functions. And what we should have to see if it could replace that function by more standard. So just to explain I will cover the examples of Semiclassical ratio for closed rules. In fact, also about Semiclassical ratio on domains. So if okay, so the closed domain on full, we know that the scope for the functions going to define the spectral type. So now we just apply the main result. Just need to domain condition, and this domain condition has been known since the late 40s by result of Minashi-Silverman opinion, which give a full short time asymptotics for the equivalent of the equation on Poisson. The particular result supplies the following that with F's continuous function. And if you look at trace of F with the x minus t with the v, so this will be like t to minus n over 2, where n is a dimension n times, so it will be like t to minus n 2 times the integral of f against n t, and you have a lower over 10, which is t to minus n 2 plus. And in fact, the result is the full asymptotics. But for Poisson, we need the first there, and I think and so okay, and then so you see that supply y. So the person gets to like so we can apply the statistical y still in the contingent to occur with Semiclassical. So in Riemannian geometry, so in particular, the person gets to also. Find my right of connection to the on the vector. Right. So, right. So let's say this is 1 hour plus question. 1 hour plus. Okay. So, right. So now I explain our thing. By this to confirm, right? Right. So confirm time of very information and so given by a series of real antisymmetric. Real antisymmetric n by n. So n is bigger than 2. And the component torus T n is meant to be the non-collective space whose algebra function, that is the algebra of continuous function, that is the star algebra, is united by in the case one satisfying this simplification. So this non-collective torus, the star algebra, c'est tout à elle, but in fact, we have to think of this star algebra as the algebra of function of some ghost. So we are to think of any particular set of and so for theta for the zero, we work over exactly the algebra continuous function of the ordinary torus. So yeah, so for theta equals 0, right? So you take j to the multiplication. So e to the 2I by xj. So this is in the of t. So these are the for theta equals 0, e to 2I pi hj. So these are the Fourier monomials and the algebra of trigonometric polynomials for us. And this is a dance. It's dance. Trigonometric polynomials dance. And likewise, if you consider monomials in the original, there are term 1 and 1, so you can consider monomials in this one way. So you have them to index, n is index, m1 and c, m1 to mn, where each mj is. So you can measure 3, in fact, you can even have an noncommutative of T3 by using this standard trace. So it's a stress on C theta n, which is that tau of 1 is 1 and tau of 1 is 0. So this is so for theta equal 0, tau of n for the 3 to pi to the minus n integral of so A is a continuous function on the plot. And Simonet has defined the inner product on A2 of TEN. You can find inner product. You can find inner product with spread. So as cos of Salu, and compare to this inner product to get so it's theta. And marginally, you can also define. Well, value can define noncommutative characteristics. And this is a simple it's the sense of the genus construction. And so in particular, the action of span by life applications is sent to a star. Right. So we actually have a dynamic. So we actually have an action I on the noncommutative force that is theta. And this action is indicated by derivation v1 through the so a function I will say that dj is I dj, and the dj UK is 0 if it's so for theta equals 0, I think J will be X. J and yeah, it should be. Well, I mean, up so. And so that smooth function on the right. So smooth function on the right is actually the space of vector that the space of smooth vector respect to the action I, and this corresponds to the chemical charge in terms of Fourier functions. So, so I didn't mention here is that the UM are from an orthonormal basis of L2 T theta N. So element in L2 of theta N and like some kind of Fourier series decomposition. Okay. And the element of the smooth operators are exactly the element of L2 theta N. In Fourier series, the coefficient of the sequence of the Fourier coefficient have as rapid. And this for star equals 0, this corresponds exactly to the characterization of smooth function of products in terms of their Fourier extension. So function on torus is smoothly founded. It's a Fourier coefficient have rapid.
What is as say then?
It's rapid decay. So it means that AM is equal to big O 1 plus N minus N for every. Okay. Okay, so let's define students right and define the question of the Symmetry, right? Or in fact, on this some maybe some stuff not for the talk, but simply to le fâcher. Ah, juste là, dans le. Ouais. Faut se fâcher avant. C'est ça. Avant, so, and what we have for the top, that close and the form of two. In fact, not only is closed on the multi, okay, so all the methods, algebras, and closed on the multi function. Okay, so we find the Laplacians as operator from simply direct to simply direct, which is divided by the sum square of the. So we kind of ordinary torus So what's the conjecture in our paper with Edward and McDonald? We actually have Semiclassical also for quantum. And so we're going to conjecture it because what we establish some estimates on quantum at one, and basically what we think about is that if you have the estimate, so if you have a Semiclassical overflow for smooth potential, then our estimate implies that this extent to potential in some noncommutative. But well, the paper was long enough, so we didn't try to prove this Semiclassical overflow. And normally it's not like it could be done by this differential technique. But in fact, we don't need this technique in both. So the third conjecture means so that we are in Q, and this is quite one element of the smooth torus. So in fact, you can replace the torus by use smooth torus. So if you look at the number of eigenvalues of H to Q of H plus V, by H and N as H goes to 0, these are the limits. which is sort of some power of negative one. So this was true for 2 equals 1 and n equals n equal to 3. When I go to Sukochev-Zanin, that's the bonds are that's equal to true of the four. So in particular, the approach that network for so n is greater than or equal to 3 is because and doesn't include n equal to because the semiclassical also for spectral tuples is only for spectral tuples that are reasonable with speed greater than. So for quantum 2 to us or 2 to us, for quantum 2 to right, you get reasonability with speed equals first doesn't allow us to get spectral value for quantum. And in fact, now we can actually apply result motion work. So can show that square root of delta gives spectral tuples. For spectral tuples, there are L as well, the smooth for us. So smooth quantum time for us. In this case, is H2 of typical time and so this can be shown by using differential calculus on right? But it's also can be shown by hands because we have a full spectral decomposition for the chance as follows. The delta of Weyl is m squared. Okay. So m squared is in one square. And then and so no all its eigenvalues, eigenvector, etc. So it can be shown by n that time is possible. So what you need to show that's for spectral triple is and square root of delta rules well, just in this. So that should be true around infinity. No, should be infinity, and then so that follows for the on this. Get spectral asymptotics for the eigenvalues. This, and you need to show that square root of delta is below A infinity. And this is not difficult to prove. It's not difficult to prove. You can prove it. And so here is spectral tuples, and after apply to the ratio for spectral tuples, you need to check that you have a covariant condition. So here we are following that if A smooth, definitely theta n, C goes to 0, look at first x minus t delta. This is like t minus n over 2. Now to sufficient for n. So here tau is the press for the press from me. So I give you the exact coefficient. And okay, and then you have a remainder term which has exponential. And this can be proved by using the Poisson solution from just a few lines. And so now in position comparison to flow, and we show that the conjecture with it's for all the Q and for all the exponent element of C. So here I set the level for the models. We can model eigenvalue of H2 to the H2, which is like H2 and at H goes to the whole solution, tau of some power, tau of some power. So that's the situation in the flat case. And I'll explain in the talk, we have some flexible also for closed Riemannian geometry. So you can define some Riemannian geometry on quantum theorem, the notion of Riemannian geometry, and we also have a notion of Laplacians in the Riemannian geometry. And so you can ask if you have a semiclassical vassal for Riemannian geometry on quantum theorem. Okay, so that's why the part of the second conjecture of McDonald. But before I state the second conjecture with Ed McDonald, I just want to explain how this kind of Riemannian geometry on term. What makes it easier on term prime is that so I define define the problem. Well, yeah. So metric. So metric, like the field of metric on the tangent space. You can also think of it as a metric on the reference. Also think of it as a function metric on the module of section of the tangent space. And what's the module of section of the tangent space? It's the module of the vector. And the vector fields are equivalent to derivation. So can for quantum, and we already have derivations on the quantum for us. Okay, this are chemical derivation one and two. And as I explained for theta equals 0, this d1 dn correspond to the derivation ddxj on the ordinary vectors. So we define the module of vector fields on typical as a field left, it's an infinity typical module guaranteed by the derivation. Okay. So again, you think of vector field as the range. So in fact, these are not all the derivation on typical, but it's the one that could also have in the and a definition of, so back to Rodenberg, Jonathan Rodenberg, that define a metric as being given by a positive matrix with a tree that are separate. And okay, so what I want to explain is that I share my metric. So this is given by matrix with a tree that is infinity to time. And so this matrix is positive. And, okay, so and so if you have a addition metric on x theta, or the following formula. So if x is coordinate xi, if y is coordinate yj, when x y the sum of xi, jj, yj. And why not call the jj actually separate one? Is because so if you know the jj, we need the product of the and so if you look at the definition of metric, we require that the inner product of real vector fields is real-valued, and what seems to be real-valued in the noncommutative setting is to be a separate. So positive invertible matrix. So if you like, so we can we have a representation of Mn of CFT in L of O2 and also Cn. Okay, and positive invertible means to be positive invertible. And it's okay because this is closed on the matrix function. Okay. Felix on example, so you have a metric, so it's ij equal to ij. So apart from probably was when you look at the second example. It's completely flat, okay? So it's considered by so it's not included by Christoph, and also traversed by various people, including Sukochev-Xiong-Zanin, that is available by me, and others. So basically, just multiply, multiply the flat metric by quality reversible element of simplicity. So there is a square. And originally, even this is really the simplest, well, another example you can take in scalar, but this is probably the simplest, not completely examples, but already with this conformal flat, conformal information of flat metric, already gets into a lot of troubles when you want to compute, already gets into a lot of. So what people have been interested in is to look at the well, so okay, well, well, I will explain later. So you can define Euler quotients. I will explain how we define the quotient, and this has a full asymptotics. Okay, and so it should be A, and this J. So it should be very simple. This way. I should not write KJ. J. J is not good. Okay, so BJ. Okay, so people have tried to compute this coefficient BJ. So even the second coefficient, so that will be B1. Okay, since so even if I want to compute explicitly this coefficient for this performance graph and it will be very difficult computation. And the reason why people are interested in this because this is so for closed Riemannian manifolds, the second coefficient will be given by the scalar curvature. So people interpret B1 as a scalar curvature for this conformally flat metric. So that's why you want to compute them explicitly, but it's also very long. And actually, I have some amount of this conformal flat example. So it's so I look conformal deformation. So this was actually you write matrix as you write yeah, so basically you write it. It's not really well anyway. Yeah, so you write well, yeah, so you write Mn. Yeah, so you write again. I'm not sure. You write matrix Mn sub C as a black matrix. Okay. And you do a conformal deformation in one. And you can also consider a diagonal. I'm not sure what's the best G. So you do conformal deformation in the blocks, but using different deformation. Well, so you want define okay. Define the Riemannian volume. So it's like the ring is a measure, still with some density. So we need to define the Riemannian density. So in fact, yeah. I'm not sure. So if you look at Riemannian density, so you choose Riemannian density. So if you look in local coordinates, this will be given by square root of the determinant of G times the Lebesgue function. Okay, so G should be G at J, or if you like, G at J. This is G of dx I of dx. So to define the Riemannian of Xiong for us, so we have to define the determinant. But the problem of the G here on C infinity or T L, G is defined by an element matrix with a trace in C infinity theta. And C infinity theta L is not commutative. So the dual definition of the determinant does not work, but we can use the fact that Mn of C infinity theta N is closed on the holomorphic functional calculus. We define the determinant as G. So it's like a Foucault-Davidson determinant is an alpha of trace of log of G. Okay, so because we should also say that in general, determinant a log of H is equal to trace of log G. Okay. Sorry, so this is determinant is X of trace of log G. Okay. And because everything, because Mn of C infinity theta N is closed on the holomorphic functional calculus, as C infinity theta N is also closed on the holomorphic functional calculus. So this actually defines a positive invertible element in C infinity and T theta. And what we are actually interested in square root, so what you get, what you take from G is exponential of 1 half of trace. So that's the Riemannian of C. Then you find the Riemannian weight of G as the integration that is so for ordinary Tori, this is integration against the Riemannian C. So here what you take is store against G. So the Riemannian weight is store of U G. And après certify to again in France normalization functions. C'est normalization function. And define the Riemannian volume as integration of the constant function of 1. So here you define G of 1, which then leads to pi N of 4. And why is pi N? It's because when you take the Dirac metric, so if you take a Dirac metric, we take G to be J, okay? So basically I will see determinant is 1, so new G is 1, so we get 2 of 1, which is 1. But 2 of 1 is not the volume of the Riemannian for us, so pi N of the Riemannian for us. So to pi N is just the normalization factor, which is used for stuff. And now we define F2 G of theta. So we find an inverse space associated with Riemannian. Okay, as a completion of C theta N of this inner product associated with the Riemannian product. So inner product is phi d of U B star times 2π so and vector of U B star. So okay, now I'm showing that this is actually the unit space, not for C theta N, but for the opposite algebra, with respect to the some normalization version of the Riemannian. And this means that you have some modular factor here. That is to get now the condition of theta N in theta N, we need to you need to combine with the square root of the number. So that is our point. So that works out function when conjugate A by G to the. So maybe I should put the formula. So inert, this is nu G minus 1/2 A nu G. Okay, so you can define the questions. So this is the formula. So this will be a operator from simplest time to simplest time. And it's about the inverse of algebraic ordinary functions. It's about the inverse of the metric. So this is G inverse is actually the G upper J. So this formula that you get, so this is similar to the formula for the ordinary functions in the coordinate, except that for your formula, we have so G is square root of the G, okay? And here you have G1i, Gij, G1i. So note that if you commute, the Gij commutes with G, so what you get is G times J, which will be square root of G. So the only difference is that we make less square root of G Gij by G1i, Gij, G. And in fact, the definition is well, depends what definition you use for the definition, but you know, this formula comes from the fact that the Kaji, we define the Kaji as a derivative, some analogue of the Riemannian function. Each action. So this definition makes sense. And if you have, so I give some examples. So take that metric to cover the flat proportion, we defined before. So minus the 1 square of the. I don't want the minus. Okay. For conformity flat metric, we have to fix it now as well. So this J is x squared beta J. What case a positive inverse, no element positive. Right? And that's it from that, it's K minus 1 minus 2, the value minus 1 constant order 1, and note that if n is equal to 2, you get the I of 1, so the I of 1 is 0. Okay. So when equal to this terms here or here, and that is K minus 1. And this the sum of the conformal balance of the functions on the surface. And you have the same, you have similar property of the function as of the function Riemannian tools. So there is the combination of the so what's important is that, yeah, so, well, it's essentially subadjoint and positive on G, and it has discrete spectrum.
So what is essentially symmetry?
But
what do you mean by essentially symmetry?
I mean, it's essentially spectrum.
Essentially being equal to compact with that.
No, I won't.
No, so
Need that closure with spectrum.
oh, okay.
Like with another definition.
No, so I don't know exactly. So if you don't consider the closure, because yes,
But I don't want to start the domain. So
yeah,
so yeah, so this is essentially simple it's infinity.
okay.
Which is that true. And the trial consists of non-negative ones. It consists of non-negative values, finitely, and the kernel in cells consists of. So exactly the same property that we have as for the channel close. And yeah, So yeah, some there's too much on this. Yeah, that's a functional calculus. So, but which works as so we associate with some kind of function. We associate with some functions. This function are called symbols. They are functions originally these are functions from Rn to Symmetry and against some topology on Symmetry. So it makes sense to have some precious space P, so we can group map with Symmetry. And yes, and it's some asymptotic functions in terms of symbols that are homogeneous. That is fly so toute la composante rho Q majeur, rho Q majeur, ça, ici on va imaginer rho Q majeur. And the process to associate the symbols operators. Okay. And so if the symbol for the Q, you get the operator of Q and class by psi Q. And so this is how it's defined. But when you get simpler when you look at differential. So for instance, if you look at the differential operator, some of the alpha, so the alpha is this. So the alpha derivation. So that's the D1 if you want for the so it's a differential operator. P, so differential operator, can you return the differential operator, therefore P rho. So P rho is the operator associated to symbol rho. And that symbol rho can place some of the electron outside. So là, this is this general. There is a distinction for that sort of definition of differential operators on including of differential operators. So as I mentioned at the beginning of the talk, there is a ratio for eigenvalue, positive and negative eigenvalues of negative order of differential operator by Birman-Solomyak, and with only one to determine another of this result for noncommutative for quantum point. So if we consider a simple operator for the minus Q or Q is primitive, so it has assume as principal symbol for minus Q psi. So to the that you have ratio for the positive and negative in the following form. So if you look at plenty of negative of P, divergent with design, goes to infinity, this diverges to this quantity. So it's some power of multiple over the sphere of tau of O minus Q psi plus or minus to the n over Q. And then integrate and take power. So this is the version of contemporary ratio for negative sequential operator. And there's a version of this design where instead of looking at positive and negative eigenvalue, we look at singular values. That's the eigenvalue of the absolute value. And this one is studied by Sukochev-Xiong-Zanin for Q equals 1 and for smaller class function. And in fact, what I want to do, I'm getting over time. Right. So I'm going to wrap up. And I'm going to
yeah, you can continue. Please have an hour for the question, but you can take
I know.
as you may.
No, I prepared so that there is this is that also.
Okay.
So what I want to explain is that you can get improve this conjecture by as consequence of it's called I mean a essence of the main result mentioned at the beginning of the lecture. But it's not a direct so because all right, the thing is the difficulty here is that I said so for closed Riemannian manifold equal to M square root delta G. We know this is the spectral triple. Now, if you want to try, you can also consider a similar triple for the quantum torus, Riemannian metric. But in fact, this is not a spectral triple. And here I see the consequence of the fact that of the non-commutativity of the quantum. Okay. The problem is that so this is this. Look at the commutator of square root of delta G. So you can define square root of delta G. Square root of delta G better with element of A. It's infinity and it's not bounded. So that's the problem. However, there's a way around this, that instead of, but of course, we know that if we use the flat, in the flat case, we have a spectral triple. And the way around it is to in fact use a larger, if you use a flat spectral triples, but where you replace algebra by a larger algebra. And this larger algebra is algebra order 0 sequential. We can ensure this is an n symmetry. So if you use size 0 instead of C infinity theta n, so the larger algebra. For size 0, c'est un peu mon chien, pas par ordre 0. Donc, size 0 of n, equal to n, as square root of theta. This is an n simple, such that. And moreover, also not difficult to show that. So yes, equal to one, and also have a covariant condition. So in the results, I gave two covariant conditions. One, I'm giving the fixed semigroup. Another one, I'm giving the stat function. So what's works here? Function. So if take basic A of the operator, it's not specific. Take a trace of A detachment D. So it's going to have a normal extension to C, which only and near C equal N, they have only one simple pole at C, which is divided by integral over Sn of tau of what's the rule? So what your sign can be value? So what is the work sign? The amount of C infinity. Okay, so we have position. So yes, we put square, satisfy to the equation, so the main result applied. So I gave two. We have two parts of the main result. One was the Weyl for some impact operator, and by Birman-Solomyak the supply simple by Weyl. So here we have the thing in the first part, and so that we get Weyl for Birman-Solomyak operators, which here take the form of the to the 4a vector minus q4, where a is a quadrant element of set 0 of t. So if take positive negative of the value, multiply by j to the equivalent, this has a limit, which equals to infinity, which is given by some power of the whole of tau of reverse power of PT on the part of all the time, where all the time is. And you can always so this what we get this is what we get by that I mentioned at the beginning of the talk. So here you have operator of the form, this works for operator of the form delta minus q over 2 a delta minus q over 2. Now, if P has order minus Q, you can always write it as form delta minus Q over 2, delta Q over 2, A delta Q over 2, delta minus Q over 2, for some finite rank. So we don't care about finite rank. Okay. And what you observe is that delta Q over 2, sorry, it's P. So we take this to be equal to A, and that would be of order. So P has order minus Q, delta Q, should be delta Q over 4. Right, that's okay. So P has order minus Q, delta Q over 4 has order Q over 2. So this has order Q over 2 minus Q plus Q over 2, which is 0. So up to finite rank operator, any sequential operator of minus Q is obvious. So therefore, we get the results that P is equivalent to inside minus Q, responsible symbol rho minus Q. Then you get by the slope for the positive and negative values. So you multiply them by J. J goes to infinity, so that gives you some power of natural over S of tau of inverse power of the positive and negative part of the polarity. That's what's precisely the conjecture with Edmund. So we get this Weyl for negative order sequential operator of function point, and another Weyl for Birman-Solomyak. And from there, you can actually get this closure slope for Riemannian symmetry on terms of line. So more precisely, you can apply now the previous level to delta G minus Q over 4 V naught delta G minus Q over 4. V naught is like this, okay? So this is sequential operator for Q. So we get the Weyl for the negative values for associated negative values. So we get some so we get an explicit formula. So the bit at least you have an explicit formula, okay? And if you combine by the Birman-Solomyak principle, then you get Semiclassical ratio for Schrödinger operator of Q plus V naught. Where V is a quadrant element of spectral plus positive there. So if you have a negative value by H as H was 0, so this. So, okay. So we have the formula. The formula is a bit connect. And but it's at least but at least you have a proof. So this gives us a slope for Riemannian geometry on contour. And if you look at a special case of from our deformation of geometry, we look at the form Gij is this way. When this simplifies, the limit you get is 100% times 100% de Riemannian. So of K, K, and we secure and simple for you.
Are you thinking about the question?
It's a lot is very interesting. Yes, I think actually I'm thinking another version of work.
Another question.
Did you try any other non-commutative method?
No. Right. Well, I look at over commutative example. What would be interesting is to, well, what also have in mind to have a setup for non-commutative opinions.
Yeah. It's exactly what I'm. Yeah.
So the
What is the difficult because it's possible like enjoying the compactions or something else.
yeah, so yeah, I'm pretty sure that at least 80% of the argument works for me. Okay, so just you have to go back to the definition of spectral. Yeah, so I assume algebra A to be even two.
Yes.
So that's yeah. So if you remove two,
But can it be replaced some approximate property?
no,
I'm not sure about it because we will assume that certain nice property approximately for this style algebra.
okay, when A is not unitary, you replace yes, it's slash function. So replace this condition by something like A, D is compact. A1 plus D square, something like that. Okay. It's yeah, well, it's something that, well, this one is compact. Or even A. And so it gets a bit more, so then the definition for the last function, it's not totally set, so you get something like 1 plus. Maybe you get something like -1. Sorry, it should be D. Okay. Well, here I can replace this by 1 plus D. It's not really. And yeah. We also over authors, which look replace this by A D minus. I'm not exactly sure which one should be used. I will be more committed to use condition like this, but and yeah, so I think if you have this condition and many of the arguments should work. I don't check for the so I've seen that only 80% works, I think for sure, and then I have to check for the remaining.
Actually, I see that this spectrum is very general.
Yes.
It's very general. Actually, a lot of things fit in this framework. Like even for finite index inclusion. I don't know if you know about
yeah.
process work.
Yeah. Yeah. So probably what I mentioned to work for C'est trop triple, par exemple.
Yes.
Voilà.
What about is there a notion of I guess like a notion of non-commutative sphere?
Yes, you can.
The your your work is working in this for this kind of non-commutative manifold.
Yeah, I'm not sure. I mean, yeah, so yeah, we have to think about that. So, but even if I'm confined, well, okay, so can you look at that element then? Yeah, yes, yeah. Well, I need to check how to make the addition.
I mean, how to define the non-commutative sphere?
No, 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 the basic definition of an question, I don't remember them. I think so. People are defining spectral triple. I think we may have some of this function, right? Yeah, so we need to get something. But what I was, yeah. No, I was thinking of the Riemannian geometry. But I think, yeah, actually, already the fact is for you. Yeah, so good. Thanks.
I think that you understand the D will be the step joint, right? So
Yeah.
what if it's not step joint? What will happen? Because we are doing something similar to this, but we are not assuming that D is step joint.
What do you mean? It's not second one? You mean
So D.
what do you mean by that? Like you want this to only be symmetric or?
Yes, something symmetry, because we use something else. We check our example, and we found that I thought my example is a spectral, but your spectral requires that D is step joint. So I found that our example does not fit your.
Okay.
So I don't know if you consider anything else about this D is not step joint.
Well, it can be such a thing, But
I know that.
If it's symmetric, I think we get into some problem. But I think some people look at, I think it's arbitrary.
Okay.
You look at the number of the symmetric properties and find a way to get some kind of determinant pattern.
Mm-hmm. Because in our case, actually, this D is a full transform of the possible of a possible elements. It's not itself not necessary to be left joint, but it has some other things from its dual. Because in your case, you actually raise the dual side. Yeah, actually, there's a dual side of this tree. I don't know how to compare our work with your work right now, but I think there may be some connection. Next one.